Welcome to this presentation on how digital and analog systems count. So it helps if you start out by thinking of what is sound, because sound is essentially a communication channel that is analog. So think about sitting in the stands and watching a parade. You've got a drum going down the street, which is a big sort of membrane, or the drum head, that gets hit by these sticks. As they get hit by the sticks, that membrane vibrates. As it vibrates, it goes ahead and creates a compression area of sound, where the sound is sort of packed all together. The air is all packed all together. And then places where there's sort of a trough, where there's less sound packed together. So if you think about the wave signal, it's something like this, where it gets hit, it vibrates, it makes a big peak of sound, or compressed air, and then on the reverse as well, when there's less air. Now in your ear, it's sort of the reverse process. You have a drum membrane again in your ear. As the air comes in and hits it, it moves this little membrane, which then triggers fluid and little bones inside of your ear, which are translated into sound. Now an analog telephone works in a very similar way. You have the same sort of signal coming out over the air. Then you have a microphone. The microphone is essentially a membrane, just like this one, that vibrates as it's hit by these sounds. It then transmits that vibration into an analog electrical signal. So rather than being transmitted over the air, instead it's transmitted over a wire. At the other end, it comes out into a speaker, which is just the reverse of a microphone, in that it takes this electrical signal and uses the signal to vibrate this membrane. As the membrane vibrates, it causes the air to move, which is then interpreted by your ear. But the key thing with this analog system is that you always have this waveform. Now digital signals are different. So we have our traditional analog signal like this, and the key thing about analog signal is that there's not just like an on or off state. Instead, you might say values, right? Say this value right here is equal to 10.1. This value here is equal to 8.725. But as you go throughout the range here, there's sort of infinite precision. Right? This number can keep on going if you've got a really, really sensitive microphone or really, really good ears. Digital signals are different. Instead of that range of values, digital signals have two possible states, on or off. So for our little waveform here, this is 1 or on, and the one here is 0 or off. There's no intermediate. There's only two possible states. So then you have to think of, well, how do you communicate information on a digital signal where you only have these two possible states? Now you might think at this point, well, how can you possibly communicate as much using two states when you have, compared to an analog signal, almost an infinite number? Think about your voice. You've got a whole range, you've got pitch, you've got high, you've got low, you've got loud, you've got soft, all sorts of variation you can use to encode information. But digital, you only have two possible states, on or off. So there actually are older systems beyond computers that use a digital on or off signal. One of the standard ones is Morse code. Morse code has only two states, on or off, and you encode information by how long you keep those states. So for example, for an A, you have a short on signal and then a long on signal. For a B, you have a long on signal, and then you have three short signals. But again, this is just a purely digital signal. The key is that you encode information onto this on and off signal, just to agree in advance what this means. Now you can find systems like this elsewhere as well. This is called a Jacquard loom. The idea is that you have a punch card with holes in it. If their hole is open, then it's a signal to let something happen. If it's closed, then it's a signal to not let anything happen. Now these Jacquard looms are actually in use today. One of our librarians at our school went to India and found this gentleman creating a really beautiful textile here on the bottom using nothing but these on and off signals in the punch cards. So then we get the question of, well, how do you count? So in a decimal system, you've got 10 possible options. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, when we get to the 9 and you want to go a little bit higher, you don't have any more symbols to use. So instead, you take the symbols back down to the first one, and you add a second column, starting at the very beginning. Binary works exactly the same way. So 0 is the same thing. 0, 0. 1 is 1. And then 2, we have a problem. We don't have any more symbols. So like in the 10 systems, when you run out of characters, you add a new column. We do the same thing in decimal. We add a new column, incrementing it by 1, and you take this and put it back to 0. Same thing for 3, 1, 1. We have room to go up, so we'll go ahead and increment that one. 4, we're out of room again. So we take the 1 back to 0, and we increment the next column. We have a problem here, though, is that we're already at the top, so we take that back down to 0, 2, and we add a new column. For 5, we can go from 0 to 1, because we can increment that again. Everything else stays the same. For 6, we can't go any higher, so we go back down to 0, and we increment the next column. The rest of it stays the same. For 7, we can go up. Everything else stays the same. For 8, we can't go any higher, so we go back down to 0. Can't go any higher, so back down to 0 and carry. Can't go any higher, so back down to 0 and carry. And 1. Now, if you pay attention to this, you see a nice little pattern forming. Right? You can kind of think of this as kind of a style of rollers. I imagine an old-style car odometer. And generally, you have a lot of numbers on old-style odometers, 1, 2, 3, 4, 5. But this is just digital, so you only have two possible numbers, zeros and ones. So as this rolls around, just imagine the numbers going from 0 to 1 and then back down to 0. And then when you get to the end, it increments the next column. It makes that one go over 2. Now there are some neat mathematical properties here. So for the first column, essentially, right, you have 0 and 1, two possible options. Okay? This is also equal to 2 to the power of 0. So if this column is on, then you add 2 to the power of 0 to your results, or 1. If this column is off, then you add 0. For the second column, you have 2 to the power of 1, which equals 2. So if this is a 1, you add 2 to your result. If it's off, you add 0. The next column is equal to 2 to the power of 2, or 4. If this is on, you add 4. If it's off, add 0. So to calculate this right here, you say, is this column on? Yes, well then we add 4. Is this column on? Yes, well then we add 2. Is this column on? Yes, we'll add 1. And we come out to 7. Same thing for this guy here, right? For the next column, it's 2 to the power of 3, which equals 8. So we say 8 plus 0, 0, 0, so we end up with 8. For 9, we have 2 to the power of 3, which is 8, plus 2 to the power of 0, which is 1. So we have 8 plus 1 equals 9. You can do the same thing to make a simple little binary clock. So for our first column, we have 2 to the power of 0, which equals 1. 2 to the power of 1, which equals 2. 2 to the power of 2, which equals 4. And 2 to the power of 3, or 8. So if this is on, then the number 8 gets added to the total. So we have 8 plus 90 of these, and this one. 8 plus 1, or 9. In this column we have 4, and then the other ones are lit, so it's just 4. In this one we have 4, 2, and 1, so we have a total of 7. We have 2 and 1 here, which equals 3. None of them are on, so it's 0. And 1 is on. So we end up with a digital clock saying 10, 37, and 49 seconds. Now once you know how to encode numbers, and when we get into other problems of how do you encode letters, or symbols, or pictures, or anything else that you might want to communicate to somebody. Well, this is an example of a simple encoding scheme. Whereas the chunks in which you think are all at least 128 possible combinations for each. So depending upon the combination for each one of these possibles, you say, okay, if we transmit number 73, then we want uppercase I. So if we want the message hi, you're going to transmit the numbers 72 and 73. Transform these things into a binary number, which I'll just simple little example here. Put those somewhere, whether it be into a network interface or from one program to another program. You communicate it. On the other end, it transfers it back into the word hi. Now you can see binary in some of the really old machines out there. This particular picture is of an Altair 8080, which was the first hobbyist computer widely available. And if you look at these little lights here, you can see each light also has underneath it a switch. The switch allows you to turn this to on or off. So to program these machines, you're going to have hobbyists come down here and they would actually hit each one of these switches. On, off, on, off, on, off. And if you notice here, there's 16, from number 15 down to 0. So you have 2 bytes, or 2 sets of 8. And you could encode a value from 0 to 255 in a single byte. And this was how they actually input their programs. So if they wanted to put the letter H in, they would put this one on, this one on, this one off, these ones off, 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 and then hit input. And the computer would then go in and store that number in memory. So it's pretty tedious and time-consuming. But this also applies to larger systems too. So here's an IBM 360. As you see though, it's a lot more complicated, but the same basic idea. You've got little lights showing on and off states. So just in the way you can with a little machine going in and look at an individual byte, you can do it with a larger machine as well. So hopefully this has been helpful in showing the basics of how computers think. Every computer comes to the same thing, whether it's your iPhone, your desktop, your laptop, or a supercomputer for NASA. They think in terms of digital signals, on and off. Those digital signals are then stored as a binary format, which lets us count. Those binary numbers are encoded with some sort of meaning by the program. So it could be something as simple as Morse Code, could be something more complex such as ASCII, or something with a modern computer would use like Unicode. But in any case, the same basic principles apply no matter it's a big or a small system.